us consider another oscillator, that is Hartley oscillator. Hartley oscillator circuit is also similar with Colpitt's oscillator. Only change is in the tank circuit. See, the left part is as usual our single stage common emitter amplifier. This part as usual, this is our amplifier, see, and this is our tank circuit. That is the parallel combination of L and C, that is called as a tank circuit. So in Colpitt's oscillator, we see that there is two capacitors C1 and C2 and single L. So what is done in Hartley oscillator, instead of using a split capacitor, here we use split inductor L1 and L2, and we use a single C. So usually this L1 and L2 are nothing but the transformer, that is primary and secondary. So this consists of primary part, this consists of secondary part. And this common point is grounded. So here also, whatever voltage developed across the coil L2 is fed back to the base of the transistor through input coupling capacitor Ci. That means part of the output energy is fed back to the input of the amplifier. Then this common emitter amplifier will amplify that small voltage and it appears at the collector in an amplified form. And then this voltage is further used to charge the capacitor. See, so whatever energy lost by the capacitor is provided by this amplifier so that the capacitor gets proper electrical energy. This is one part. The second part, that is phase, proper phase difference is essential. So here we see that the common emitter amplifier produces a phase difference of 180 degrees. I will show you with the help of diagram. Suppose the voltage appearing at the base. What we are doing here, the electrical oscillations are produced by these tank circuit, as we have studied. That when switch S1 is closed, the capacitor gets charged and it again discharges through L1 and L2. Again, the voltage developed across capacitor again used to charge the capacitor. So charging and discharging of the capacitor process starts, electrical oscillations are produced, and these are damped oscillations as we have seen. So we must have the sustained oscillations. So we have to provide the energy to this tank circuit. So that purpose we are using an amplifier. So whatever energy fed back to the amplifier gets amplified and it is again given to the tank circuit so that the charging of the capacitor to proper value takes place. Then phase difference. If we consider that this is the feedback voltage coming at the base of the transistor, when this voltage appears in the collector at this point, there is a phase difference of 180 degree that is produced by common emitter amplifier. So you will get the signal like this. See, here positive cycle, here we are getting negative cycle. Therefore, there is a phase difference of 180 degree. Now, if you consider this as a point P, as we previously discussed, the polarity will be like this. This point is positive, this will be negative. Means, when this voltage passes through this tank circuit and appear at the base, what is the polarity? It will be again 180, phase difference will be there. So it again goes here like this. So see now, this voltage and this voltage, they are in phase. So there is a positive feedback. So that condition is satisfied. For an amplifier circuit to work as an oscillator, there must be a positive feedback and that is satisfied. And therefore, when the Barkhausen criterion, that is A beta is equal to 1, is satisfied, then the circuit starts producing the electrical oscillations at the collector. So we get the output voltage, AC voltage here, this point. Again, in Hartley oscillator, the output waveform is sine wave. Therefore, this is also a sinusoidal oscillator. So you can't produce a square wave by using this type of oscillators. Like Colpitt's oscillator or Hartley oscillator, we produce an output voltage which is of sine wave, or the shape of the output is sine wave. And therefore, all these oscillators are called as sinusoidal oscillators, which are very much required in TV and radio receivers and transmitters. So what is the formula? Same formula, just like as a Colpitt's oscillator, F is equal to 1 upon 2 pi root LC. But in Hartley oscillator, there is a split up inductor, that is L1 and 2. In Colpitt's, we have seen that there is a split up capacitor C1, C2. Therefore, we have calculated equivalent capacitor between point P and Q, that is C. Similarly, here we are using split up inductor L1 and L2. Therefore, we have to calculate the equivalent self-inductance L existing between point P and Q of the circuit. So this is usually a transformer, primary and secondary. So equivalent inductance L is given by L1 plus L2 minus 2M. And with this formula, you can calculate what is the frequency of the Hartley oscillator. This oscillator is again a high frequency oscillator. Colpitt's oscillator is also high frequency oscillator. The Hartley oscillator is also high frequency oscillator. The advantages of these Hartley oscillator are it is used in radio and TV local oscillators. In a demodulation process, we require a local oscillator in radio and TV receivers because the signal received from the antenna of the radio receiver is in the kilohertz or megahertz. So that should be brought to the audible range. Then we can listen the audio through the speaker. We can't listen the frequency of megahertz. Human ears are not sensitive to a megahertz frequency. The whatever frequency received by the antenna of the TV or receiver radio is in kilo or megahertz. So that should be brought down to the audio range, and that is done by using the local oscillators. So local oscillator circuits are designed by using either Colpitt's oscillator or by using a Hartley oscillator. It is used to produce high frequency above 1 megahertz. So this is again a high frequency oscillator.
If you like this video, don't forget to subscribe, comment and share this video with your friends. Thank you for watching.